So my computer just blue screened to death while we were in the middle of this. So let's give this another try. So for homework 4, part C, it has 3 parts. The first part is using the final value theorem, show that with a PI controller, a second order process with a measure transfer function of 1 will always reach the desired set point. 2. A system exhibiting inverse response has a process transfer function of GP equals 2 over 10s plus 1 minus 1 over 2s plus 1. Using Roth-Hurwitz analysis, determine the limits of stability for a proportional only controller in response to set point changes. What the hell? Assume the measurement transfer function is 1. Oh my gosh. What? And then for part 3, use simulations to demonstrate the limits of stability determined in part C2. So this is going to be very similar to homework video part B. We're going to go and derive, we're going to use the Roth-Hurwitz analysis, and then we're going to code. And behind me is the board, and we will be writing on that right after this. And hope we have no more computer issues, because that's a pain in the butt. All right, welcome to homework C part 1 board edition. So there's 2 different ways we're going to look at this. Well, we're going to look at this first, as this is basically, again, the loop of the system. Oh, I got my move goal for the week. We start off with our y set point. This is very similar to part B. We have our error, which is then calculated from the difference between y and our y set point, going through a measurement device, which we have labeled GM. Then your error goes through your GC, gets a value, goes through your GP, and boom shakalaka, you get your new y value. But this is a PI, I think it's an integrating integral controller process something whatsoever. And it's basically ran by this governing equation here, where C, so our big Y, equals C bar, so our new C equals our old C, plus KC, our controlling, times the error plus 1 over tau times the integral of 0 to time to multiply of error d tau, which is weird and ugly. But anyways, again, this is a transfer function. Well, we need to make it into a transfer function. So what do we do? Deviation variables. Exactly, I know you said it. So C minus C bar equals the brand new spectaculous C prime, which equals KC times parentheses error times 1 over tau 1, the integral is 0 e dt, which brings me to my next point. If we're going to take the Laplace transform of stuff and things, we got to know what happens if we take the Laplace transform of 0 to e d tau for t. May have done this before. If not, Google it. But the Laplace of a function with no power or all that equals 1 over s to the Laplace version of it. So this is e, should be y in this scenario. 1 over s times big Y. So now we're going to Laplace the crap out of this. So we're going to get big C equals KC times error times, wait a second. Anyway, times error times 1 over tau 1 times error over s. Yeah, that. Oh, I see what happened. I replaced this addition sign with the multiplication one, and that's what set off my radar. Oh, what is the light? Light is going weird in here. Anyway, so that's the Laplace version. But now, we also know some other stuff about this thing. We know that, oh crap, I'm going to get this wrong again. Error equals, I got this wrong in video B2. We're going to say it's set point minus y. We know its GM value equals 1. Oh, also, so we have big C, but now we want to get GC. GC, I think that's the right G value, whatever thing. Could be GP. GC is this without the error. So it's going to be KC then times 1 plus 1 over tau s, which equals KC plus KC over tau s, all in one Laplace domain. All right? Crap, I forgot where we go after this. Forget what, shoot. All right, this is what if I remember correctly, we're solving for y. So we do y, because we're going to do this funky dance here again. E times GC times GP times GM, perchance. That's 1, so we can just say screw off. But shoot, now I'm confusing myself again. But let's say we replace, we're going to replace E with YSP, so it'll be Y equals, God, my handwriting is atrocious, YSP minus YGC times GP times GM. Again, don't know why I'm including this. Divide that across. Yeah, Y over GC GP GM equals Y minus YSP minus Y. So then we're going to add that across, divide this over, so we end up getting Y equals, wait, let me do this in my, I can't do this in my head, so we go plus Y, factor that out, so you have Y 1 plus this kerfuffle, so it'll be GC, GP, GM, or 1 plus GC, GP, GM. But I don't think this is right. I think I messed up. I think I'm missing an error somewhere, or we replaced the error. This isn't. I'll be right back, because I think I messed up somewhere in my algebra, or I'm just messing up with my terms in the first place, and it's not canceling the way I envisioned it in my brain. So I'll be right back, and we're going to see if this is right. I made a mistake, because, yeah, my mistake was this is times GM, and this is not, which is kind of a pain in the butt. So we're going to redo all that. I do not like the way that sounds. It's disgusting. So y to GM times GC times GP, right? So we're going to get that over. Y over GC times GP. Because what we're going to do, we're going to solve for y. Wait a second. Oh my gosh, am I an idiot? I might be an idiot. Oh, I'm confusing myself now. I really am confusing myself now. But who cares? We're just going to keep going, and if it comes to it, you get to watch more video of me talking to myself in a room on a Sunday at 4:30 in the afternoon. Equals YSP times GM. Oh, YSP minus YGM. Add that across. So this is mathing. Anyway, so we have YGM plus sorry. I'll be right back. I feel like a dummy. I'm confusing myself with just math. I figured out where I went wrong again. But what happened was I was getting ahead of myself, where I wanted to solve for y right away. But we need to solve for e first. So then we can plug what we get here into there. So, yeah. Let's see. So we're going to do this. E equals y set point minus E times GC times GP. Get that over, so we're going to have E plus EGC GP equals y set point. Factor out E, 1 plus GC GP, and we end up getting E equals y set point. If my y's start to become lowercase, it's because it's easier to write. This still means everything's in Laplace transform mode. I'm just lazy. 1 plus GC GP. I lost GM again, dude. I keep losing GM. GM. Okay. GM. Boom. That's what we want. Now we're going to shove it back into the equation on the far side of this. So, bang, yeah. So, we're going to have y set point over 1 plus GC GP GM, it's so annoying to say, equals y set point minus y times GM. Okay. So now we have to factor it all out. So what we're going to do is we're going to add this mess to this side, subtract it to this side, so we're going to get y GM equals, YSP minus YSP over 1 plus GC GP GM. Dang. This makes sense in my brain, so it means it's probably not right. Yeah. So now we're gonna, we can factor that out, right? I'm trying to remember, would we get rid of the GM? Like, what's the best way to go about this? Yeah, let's factor out the 1. So we have YGM equals YSP, 1 minus 1 over 1 plus GC GP GM. And we don't like that, so we're going to bring this to the top. Yeah, so we're going to have YGM equal to YSP, and then it's going to be, because we want this to have a common denominator, so we can kind of reduce this. So we're going to 1 plus GC GP GM minus 1, which cancels, and then we're going to divide by GM. So we have y equals YSP, 1 plus GC times, oh man, my world is spinning, times GM minus 1 all over GM. We got a plus 1 and a minus 1 in the numerator. You know what that means? They're dead. Then we have things multiplied, and same thing on the denominator. You know, we get cancel. So we get y equals YSP times GC times GP. It sounds right to me. I'm going to double check this, because after this, I think we're close to being done with part A, for part 1 of homework 4, part C. My algebra was wrong. I lost some terms, so we're going to squiggle. I lost terms here. So what it should be is we have here, we're going to write it here actually. We're going to have YGM equals YSP 1 plus GC GP GM minus 1. And I forgot, it doesn't get rid of everything on the bottom, it just makes it that way. 1 plus GC GP GM. Oh god, my handwriting, it looks like a 6. All my G's looks like 6s right now. I don't care. Yeah, and so what happens is the 1's cancel, right? So we have that, and then we have a GM. If we're going to divide it across, that's technically a G. We can basically get rid of a G on each side, because it's all multiplication. So we're going to have Y equals YSP, then times GC times GP, all over 1 plus GC GP GM. And that's the correct equation. So what's going to happen next is I'm going to erase all of my work, because a lot of it's wrong, and then we are going to actually break it down into more of its base terms, and we are going to, again, see its stability, is I think this part. We're going to basically solve for the part A. We're almost done. We're going to prove that using the final value theorem, that was it, that everything works. So I'm going to erase everything, I'm going to rewrite this over there, and then we're going to have a lot more room to work, and hopefully only one more cut. So as you can see, I erased the board. Actually, I don't remember the last clip I made. But anyway, I erased the board. Oh, it's going to start raining outside. FBT, the final limit theorem, value theorem, is the limit as s approaches 0 of a function times a of s, a over s times s equals your y value of your function at infinity. The gist. All right, but we also have what we just calculated, y equals gc times gp over y set point over 1 plus gc gp gm. Also, when we were calculating gc earlier, we found that it equals to kc plus kc over tau is. You can also rewrite that as gc equals kc times tau is plus 1 over tau s. Just another way of rewriting it, it's easier. Basically, it's going to help us. And then, we haven't been given GP, but because we were told it's a second order problem, we know that it is equals to k over tau s plus 1 squared. So now we have all the building blocks. We're going to put it together. So we're going to have, let's see, GC is KC, then tau s plus 1 over s tau I times k, where is it? K over tau s plus 1 squared over 1 plus GC is the tau is plus 1 over s ti. God, my handwriting is atrocious. That times k over tau s plus 1. Did I forget? I forgot the kc. Times kc k over tau s plus 1 squared, and gm is 1. So we're just going to nip that in the bud. All right. So what we're going to do, I'm not rewriting this. So we're going to apply limit theorem here. So let's look. As so we have as s approaches 0, but there's going to be an a down here. That's a, leave a b. So we're going to have, let's look. S approaches 0. This is going to be infinity. Well, this is going to be 0, right? So this is going to be negligible, but we're going to have 1 survive. So we're going to have, yeah. So we're going to have k c k times 1 over s ti over 1 plus, same deal, k c k over 1 over s. My taus, I think they gave up, like right here. Looks like they started becoming t's, but no biggie. Okay. And this is the limit as s approaches 0. So unfortunately, we have to do L'Hopital's method, whatever, because it's infinity over infinity, unfortunately. Or we can use critical thinking skills. So let's think. As s approaches 0, this gets really big, so is this, so it blows up. Meaning, essentially, our 1 is going to be negligible as we're approaching our limit, as we're approaching 0, right? That makes sense. We get a gigantic number in the denominator. How much is 1 going to do? Not a whole lot, hopefully, right? So that ends up giving us the exact same thing on the numerator and the denominator. So we can just say they cancel. So we can say the limit equals 1 times a. And a is our value that we were given at the beginning of the time. We say, hey, is it ever going to reach its value? A is that value. So what this is saying is, yes, it will reach its time. Well, no, not that. Well, that's exactly what the math is showing. Is yes, eventually we will reach our value in a given time, as shown using this method. But yeah, I will erase the board, and I have to rewrite the Rouse-Hurwitz, whatever the heck it is, equation, because I forgot it already. And yeah, for part C2. Welcome to homework for part C, part 2. There's going to be a lot of algebra and a lot of writing. You will not be able to read any of it because my handwriting is atrocious and I will have to fit so much it will be small. I will say it. You can read it. Power to you. I'm sorry if you can't. But let's get into it. That was just a disclaimer. We've got a loop controller thingy where it goes that way, that way, that way. We're going to call this 1 and we're going to call this 2. So it goes, and we're told that GP equals K1 over tau 1 s plus 1 minus K2 over tau 2 s plus 1. And now we're going to make that look better. So we're going to have GP equals K1, then tau 2 s plus 1 minus K2, then tau 1 s plus 1 all over tau 2 s plus 1 times tau 1 s plus 1. All right. Sorry, I got text message. Now, we're going to do some more, because what we're going to end up doing is actual math. So, if we actually plug it in to the loop like we've practiced in the last few parts, we're going to multiply the whole thing on the top. We're going to do, this will be a denominator and numerator. The numerator is only going to be multiplied by kc. The denominator is only going to be multiplied by 1 plus kc times all that crap. Also, for this example, gm is 1, so we're just going to say, forget about it. That's just another variable we don't want to do because we're freaking tired of variables at this point. So, we're going to have kc times k1 tau 2 s plus 1 minus k2 tau 1 s plus 1. Sorry, it's just making me sad having to write this all again. All over tau 2 s plus 1 times tau 1 s plus 1. What the heck is that? Now, 1 plus. 1. Oh shoot, wait a second. It's the same thing on the bottom, I think. Yeah, just 1 plus kc k1 tau 2 s plus 1 minus k2 tau 1 s plus 1. Oh my god, I'm going to lose my mind. All over k1 tau 2 s plus 1. I did not have to write k. I'm going to lose my mind. Times tau 1 s plus 1. All right. This is what's going to happen. Everything is going to cancel except for what's right here. So it's gonna be okay. But yeah, this is all just one giant thing. Isn't that just a pain in the butt? So we're gonna get tau 2s plus 1 times tau 1s plus 1. Multiply, multiply. Now we're gonna get plus kc k1 tau 2s plus 1 minus kc k2 tau 1s plus 1. And so the reason we're doing this is so we then will have things to put in the, gosh, I always want to say the von Neumann stability analysis, the Ruth Hertzowitz, I can't remember the name and I don't know how to pronounce it. It's Jewish, I don't know. But now we're going to do the math. So for here, let's start. It's going to be, so it's going to be s squared, right? So this will be, nothing else will be s squared. So it'll be tau 2 times tau 1 s squared, I think, plus, okay, so now it's going to be just tau. Oh, I don't like doing this. This hurts my head. So for s, wait a second. Is there even anything going to be in the 0? Is this going to be squared 1? Because, like, hear me out. KC's, who cares? K1, K2, S, oh, it'll be the 1, maybe. Yeah, no, yeah, maybe. Anyway, KC, K1, tau 2, minus KC, K2, tau 1. And this is S, I think. And then I always like doing plus. I hate doing negatives. It just makes me mad. And then this is going to be KC, K1 minus KC, K2. And that's no S. The sad face. So I don't remember the stability equation off the top of my head. I know it's blah, 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 blah. And also, I don't know if my algebra's right. So we're going to be back, and I might move things around so we actually have room to do some work, and I'll be right back. Okay, I've made one mistake. We got to add T2 plus T1 into the S. It's because there's an extra term I just missed, being dumb. It's usually, squared, it's 1, 2, 1, so it would be, anyways. We have our terms. So for our first one, we have T2 times T1, and then our next one is this lump. That's not even a thing. Sorry, this is going to be 0. This one's easy. Oh, and we have to do plus 1 because we did. So KC K1 minus KC K2 plus 1. I know. And then we're going to do tau 2 plus tau 1 plus KC K1 tau 2 minus KC K2 tau 1. All right, and we want B. We want question mark. So what this is, we do A2 times A3 minus minus A1 times A4 divided by A2. So theoretically, it's just A2 times A3, because this is going to be 0, divided by A2, so we just get this lump of lard. So this equals KC K1 minus KC K2 plus 1. All right. Now, we got to see if all these are positive. This one, yes, that's an L, but yes, this one's positive because, again, it's time. Time can't go backwards. We're not in a movie. So now, we got to figure this out. Luckily, we have numbers, I think. Yeah, so we're going to solve for KC. So this is going to be greater than 0, so KC is then K1 minus K2 plus 1 is greater than 0. Subtract and then divide, so we're going to have KC less than negative 1 divided by K1 is negative 1, bang, and then K2 is, wait, K1 is 1, K2 is negative 1. Yeah, this K2, K1. And I think I did my math wrong. I think I did my math wrong. Wait a second. But yeah, anyway. I think I'm missing a value, just because like its number isn't making sense in my brain for what I think it should be. I'll do that. So the reason my algebra wasn't working, and it took a lot longer than I think it should have for me to realize this, was because I thought one of the k values was supposed to be negative. No, that's just the way the world worked. So KC would equal negative 1 over K1 minus K2, which means KC has to be greater than negative 1 over 2 minus 1. So KC is greater than negative 1. Perfect. Now, the next one is, where is it? This son of a gun. So we're going to do, I'm trying to give myself some room and hope my thing doesn't die. So T2 plus T1 plus KC, we're going to factor out KC, and K1 tau 2 minus K2 tau 1. So, and then it's greater than 0. So now we're going to bring this over to South Beach. So we have, I'll just erase it. Yeah, so that's what it's supposed to look like. And now we're going to have negative tau 2 plus tau 1. And now I'm just going to plug in numbers, like KC, and then we got K1 times tau 2, that's 4, minus K2 is 1, minus 10, that is then, what's T1 plus T2? 12, greater than negative 12, negative 6, 2 negatives. So then KC, wait a second, yeah. KC is then going to be less than 0. So 12 divided by 6 equals 2. So, my bad, yeah, equals 2. So KC is going to be, KC has to be in between 2. I don't remember how these numbers are. Oh man, I haven't done a stupid, it's like a number line thing. I haven't done those in forever. So 2 is greater than KC, and KC is greater than negative 1. And that is the stupid name stability analysis thing, which you can now go code and prove that we're right and they're wrong. And if this algebra is wrong, I'll be right back. But it doesn't look like it, so I think we're good. But yeah, that is homework, oh gosh, 4C, part C, part 2, done. All right, we can finally get to the code portion of this. So I already copied and pasted all the important crap, and then here's kind of what we derived beforehand. I'm just lazy, and sometimes I forget the equation, so I kind of put it in beforehand, because again, I don't feel like looking over my shoulder, seeing if I wrote it down, and even if I didn't, I'd be annoyed. But we need to set a KC value, which is going to be, our bounds are 2, I still have the word, 2 to 1. So we're going to set it at 0.5 for now, and then we're going to change it as we go. So now we're going to do t comma y equals sim, right? Sim, say, GCL, comma, lambda, what was it, t, lambda t, and then n equals 1000, and then dt equals 2. Don't break, don't break. Oh man, I was hoping I'd get it first try, but who cares? Fig equal make underscore subplots. Gosh, my back hurts. Okay, I'm recording. And then we're going to do, oh god, right? Is it fig dot add underscore scatter? And then mode equals lines. Let's see. No. Yeah. Takes 0 proportional. Let's see what GPT says. Explain error. Because I'm not gonna complain. I just think I'm missing something dumb. Oh, are you kidding me? I put the S. Oh, are you kidding me? Cannot convert expression to float. Well, let's see. Explain it now. AI. Okay, so it's expecting a numerical, but it's not getting a value. Let's try this. No object has no attribute, add scatter. Huh. What? What do you mean? Alright, I'm going to double check this is correct, and then, again, I think I'm doing something really dumb. Like, I don't know what I'm... Anyway, so I'm an idiot. Just plain and simple. You know, the most important thing. Oh, well, look, at 0.5, it gets to a value and stays there. Let's try 1.5. Same deal. Alright, let's try 1.9. Alright, still works. Let's try 2. See what happens. Oh, it's not breaking. Alright, see, it's consistent. Actually, it looks kind of cool. But if we go to 2.5, it's going to be mad. Right, look at that. Oh, only to the 56th power. Ew. Alright, now let's go to the negative direction. Let's do negative 0.9. It's going to be close, but it's not going to break. Like, there we go. See, it gets to a value and stays there. But if we do negative 1.1, that's not what I wanted. It goes to really scary places we don't want to go. We go to negative, let's just try negative 1.5, because that's kind of where we were last time. Yeah, that's just going to continue going forever and ever and ever, no matter what. So that really kind of shows the stability. I think, oh, also it's in the trillions. I didn't even realize that. Let's see. 60, yeah, it gets in the millions really fast. So it's unstable after -1 and after 2, which is, again, what we showed, which is still on the board behind me, if you might be able to see. But yeah, that means we have used a simulation to demonstrate the limits of stability determined in the previous part that we did on the board behind me. So thank you for watching.